Hello everyone. So in this video we're going to begin to talk about chapter 10, which is two-sample inference. So in chapters 8 and 9 we talked about confidence intervals and significance tests or hypothesis tests for the one-sample case for both p and mu. And in chapter 10 we're going to go over the two-sample case. And so what I mean here is instead of taking one sample and doing our statistics with that one sample, we're going to take two different samples from hypothetically two different populations and try to do inference there. So the methods that we're going to use and the overall approach are going to be exactly the same as we did in chapters 8 and 9. The only thing that's going to change are the symbols and some of the distributions that we work with. Okay, so let's see the outline. So first I'm going to give a short intro to two samples, which it'll be short because I probably did most of that in the first few seconds of this video. And then we're going to talk about inference for two population proportions. And to be honest, I'm going to skip over it. I'll just mention it and go by it. Then we'll talk about inference for two population means, which is what most people do or use in real life. And so inside inference for two population means, we've got a number of different cases. And the two different cases that we'll talk about, there's three in total. Two of them fall under independent samples. So that means that each sample is independent of each other. And then we have two options, and I'm going to call them pooled and unpooled. So we'll see what that means in just a second. And then the last thing that we'll talk about are dependent samples or paired. So we're going to talk about really three different types of confidence intervals and hypothesis tests: unpooled, pooled, and paired. And so we'll see how they differ and how they are similar. So to start off with two samples, many of the more interesting questions that we try to answer, or that you really try to answer, that are interesting to think about, are going to involve two or more samples. So usually I'm not interested in just one population. I may be interested in how two populations differ. That's where most of the stuff comes from. And so to do that, we have to take two or more samples. So we'll talk about two samples here, and then we'll talk about more than two samples near the end of the course. So what type of questions would you ask in a two-sample case? Well, for a sort of a toy example that really has no life consequences, but is still interesting, are do sophomores or juniors have higher GPAs? And so, of course, if I had access to all the grades, I could find this question, but find the answer to this question, but I don't. And so I'd have to take samples of sophomores and juniors and then compare them in some way. Now, for maybe a more substantial or more high stakes question, I could ask, will a new drug be effective at reducing high blood pressure? So in this case, I would have two different groups, a placebo or maybe a standard of care, and then my new experimental drug. And I apply the drug, see what happens, and then I have two different samples that I need to compare. And so that is where this two-sample inference comes in. Okay. The general strategy, as I said before, the general strategy for solving these problems is exactly the same as the one-sample case. And I'm sorry for the comma that's sort of out of place there. The only thing that changes are the symbols and the assumptions that we're going to use. Okay, so let's move on. The first case that the book talks about in chapter 10 are the difference between two population proportions. And so I give sort of the outline of what would go on here, and then I skip over the rest because, to be honest, I usually skip it when I teach it, and so I don't feel like talking about it, so I'm going to move on. But we have two population parameters. They're both proportions, and we're looking, or the inference that we're doing is looking at the difference between the two. So that's for everything, not just two population proportions, but all two-sample inference. So the example is, if I have two population proportions, P1 and P2, I'm looking at the difference. So you might ask, well, why are we looking at the difference rather than looking at the two separately or something like that? And part of the answer is that that would be harder to link the two if I look at them separately. But if I look at their difference, then I can still tell everything that I could tell in the one sample case by looking at the difference. But instead of a number, any specific number, maybe in chapters 8 and 9 for proportions, what's usually of interest is a majority, or p of 0.5. Well, here, and in the means case, we're going to be looking for a difference of 0. So a difference of 0 says that there's no difference. A difference of greater than is going to say that P1 is greater than, and then a difference of less than is saying P2 is greater than. So we can still say everything with sort of one equation rather than looking at two separately. So that's why we do the difference. Hopefully that made some sense. Now, confidence intervals and hypothesis tests for the difference do exist, but we'll skip over them. As I said before, they're less popular than the inference for means. If you really want to look at them, if you're really interested in looking at the difference of proportions, they're in the book, and so feel free to look at them, but I'm going to skip over that here. Okay, so now we'll move on to section 10.2 and 10.3, which are two sample inference for means, and it's the independent samples case. Okay, so that means that each sample that we take is independent of each other. So in my original question, my first toy example, do sophomores or juniors have higher GPAs? Those two samples are going to be independent. Okay, and so this definition of independent may be slightly different than the independence that we talked about before and that we'll talk about later on. Here it means, as independence always means, that the two have sort of nothing to do with each other, or one does not affect the other. And certainly if one group is sophomores and the other are juniors, they're not going to have anything to do with each other. So that first case would definitely be independent. So that's what I mean when I say independent samples. So, okay. The interest that we always have when we're doing two sample inference is we're trying to make inference about the difference of the mean. So that's pretty much what I was talking about in the last couple slides, but I'm going to point it out at the top of each case just to let you know that that's what we're interested in. We're interested in the difference in population means. So if there is a difference in truth, so the means are like these true things that we probably will never know, but we're hoping to make some inference about, some guess, educated guess. So of course we don't know them, and it's probably not easy to find them using some sort of census-like tool. So what we have to do is we have to take samples. And so we take samples from each population of size N1 and N2. And we don't, the N1 and N2 do not have to be the same. So they don't have to be the same, but we take samples from each, and then how do we do the same sort of stuff that we did in the last couple chapters, confidence intervals and hypothesis tests. That's what we're getting to. But first, I need assumptions on the samples that I've taken. Okay, in this, you'll notice that each of the situations that I talk about, they're going to be very similar. Where they sort of change are in the assumptions. And so the especially important ones I underline. So the assumptions that we have are that the samples are independent. Great. The second one for this case is that there are unequal variances. So at the beginning, I mentioned pooled, unpooled, and paired tests and intervals. In this situation, we're going to talk about the unpooled. Okay, so this is the unpooled situation. So we have independent samples. The variances, or standard deviations, if you want to think about it like that, we usually think of standard deviations, but in my work, I usually think of variances, and so that's why that they're here. Unequal variances means that we don't assume that both of the populations are spread out as much. So for instance, this might be a good assumption for that first toy example. Do sophomores and juniors have, which one has a higher GPA? You may try to reason yourself the way through. Here's my reasoning, is that probably in your first year as a freshman, the distribution of grades are probably really spread out because you have some people that aren't ready for college. They come in, have lower GPAs. Some people come in, are really prepared, have really high GPAs. But as you take more and more classes, unless you sort of fail out, the GPAs are going to come together. So some of the really good people will have some hard classes and get some lower grades. The people who aren't prepared will become prepared, get better grades, and you see less variation in each year that you go up. And so, for instance, in my case, it may be reasonable to assume that juniors and sophomores do not have the same standard deviations or variance. They aren't spread out the same. Okay, so hopefully that made sense. Unequal variances. And then the last one are that both populations are approximately normally distributed. So this should be similar to Chapter 8 and 9 assumptions for means, which said that the one population was approximately normally distributed. Okay, now it's both. So with two samples, we just added that both, not just one of them is. Okay, so when we take our samples, a number of statistics are created that, of course, we're interested in, just like we were interested in the one sample case, the sample means and the sample standard deviations. And so that's X bar and S. So X bar is the sample mean, S is the sample standard deviation. Now I just have subscripts to denote which sample that they're in, 1 and 2. So as a reminder of where we were and where we're going, the really important thing about, or the really important sort of idea that these confidence intervals and hypothesis tests count on is the sampling distribution of the sample mean for problems with means, and then proportions with problems with proportions, of course. But here we have that the sampling distribution of the sample mean was normal with a mean of mu, standard deviation of sigma over the square root of n. Now, of course, when we substitute in S for sigma, which is what we did, it's no longer normal, it becomes a T. Okay, so just keep that in mind, but that was our sampling distribution, and then the standard error of that sampling distribution when we substituted S in was S over the square root of n. Okay, so how does that translate to the two sample case? Well, it translates pretty directly, or how you would probably guess. So here, if we're interested in inference about mu1 minus mu2, the statistic that we're going to be interested in is x bar 1 minus x bar 2, the sample counterpart. And so we can get a distribution for that statistic. It's also normal, and it has, as you would suspect, a mean of mu1 minus mu2, and then the standard deviations, you'll see, are just basically added together. Okay, and so when you substitute S in for sigma for the sampling distribution of x bar 1 minus x bar 2, you get this. Okay. All right, so this is the unpooled inference part. So we can make a confidence interval, and I'll go through step by step, but we have talked about it quite a bit in chapter 8, so it should be fairly familiar, and I'll point out where the differences are. Okay, we're estimating mu1 minus mu2, just like we were estimating mu last time. Okay, and the general form of the confidence interval is the point estimate plus or minus some confidence factor or critical value times the standard error of the point estimate. So we know most of this. Okay, and as in the one sample case, that confidence factor is going to come from the t distribution, not the normal distribution. Alpha is found the same way as the one sample case. Okay, so if I have a 95% confidence interval, alpha is 0.05. And then you divide by 2 for a two-sided confidence interval, and so you'd get 0.025. Okay, so alpha is found just like in the one sample case. And then the other thing that you'll remember is for the t-distribution, you needed degrees of freedom. And so in the one sample case, that was really easy. I just said it was n minus 1. Well, in the two sample case, at least in the unpooled variance or unpooled standard deviation option, it's quite a bit more complicated. Okay, and so there's a whole formula that calculates it. It's called the Welch-Satterthwaite formula. Okay, that's quite a name, and it looks like this. All right, so there's a lot of symbols there. If you look through most of the stuff you've seen, but I'm sure it makes no sense to you. It doesn't really make much sense to me because I haven't studied y the way it is. I kind of just go with the flow. But that's really complicated. The important detail is that I will never, ever, 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 ever make you calculate that. Okay? We will always use some type of statistical software to calculate all of this. So you never have to worry about it. I just knew that your life wouldn't be as enriched if you didn't see it. So I had to show you. All right. That was sarcasm. Now, we'll move on. That's that. And so now we know that confidence factor is formed just like before, okay, just like in the one sample case for means, but now the degrees of freedom is really hard to calculate. And so we get our confidence interval, right, which is just as you would think. It's the same as that general form up there, but everything's substituted in. So you have your point estimate, x bar 1 minus x bar 2, plus or minus some t-score times the standard error I talked about before. Also, I'll never make you write out for this two-sample case, I'll never make you write out like the t-score, okay? And do the calculations on your own. Both StatCrunch and Minitab calculate the intervals for you, and that's going to be fine for our purposes. Okay, so there's that confidence interval. Now, I'm not going to show you an example because I'm going to make a separate video where I go through and show you how to do this on Minitab. All right, so that's a confidence interval, and the book provides this nice summary, okay, of the assumptions and the method. Okay, and so if you want to look back at these slides, but you don't want to go through all my stuff, and you just want to see the summary that the book provided, I'm going to show you it for everything that we do. All right, so special considerations for these confidence intervals, and this really moves over to the hypothesis tests as well. The interpretation of the confidence interval is the exact same as the interpretation of the one sample case, but now the quote-unquote magic number is 0. And I talked about this before, that a difference of 0 means no difference, okay? And then greater than and less than imply some direction. And so here's a nice graphic that the book provides that talks about what you'd sort of infer about a confidence interval. So especially in this section on the worksheets that I'm going to make you do, and even on the exam that you just took, I try to make a connection between the confidence interval and the hypothesis test, because they are two ways of doing the exact same thing. Okay, and so you can actually make hypothesis test decisions with a confidence interval. And so hopefully that's starting to come through just a little bit. We'll have more practice with that, but there is sort of this duality that happens with confidence intervals and hypothesis tests. And so certainly if the entire interval is less than 0, this leftmost case of the picture, then you would have to infer that mu1 is less than mu2 because you took mu1 minus mu2. That was your that was the thing that you were interested in. That was the parameter of interest, was mu1 minus mu2. If it contains 0, then it's plausible that they are the same, and then if it was all greater than 0, then you have to infer that the first mean is greater than the second, because the difference is positive. Okay, so there's that. And then the other important consideration that you have to make is that the group labeling mu1 and mu2 are arbitrary. So you've got to make sure to keep them straight. If you were interested in seeing, if you really thought that juniors had a higher GPA than sophomores, and you said juniors are mu1 and sophomores are mu2, you've just got to keep in mind that fact when you start to do the inference, and you don't switch them up and make the wrong decision. Okay, so that was confidence intervals. Hypothesis tests work the exact same way as before. They just have slightly different formulas in them. So the parameter of interest is problem specific, but it's always going to be the difference in two means. The null and alternative hypotheses are always going to look like this. The null hypothesis is always that the two means are equal, and then the alternative has the three different options as always, each implying something different. The level of significance is always alpha. The assumptions that we make, they're slightly different. The data was taken randomly. That's the same as before. Independent samples from each population with unequal variances. That's important in the unpooled case. And then, of course, approximately normal population distributions. All of these are the same as with the confidence interval. And then the biggest change is step 5, the critical value or test statistic. And so the test statistic is this. Very similar to what was before. It always has this form. The first part of the numerator is the parameter of interest, x bar 1 minus x bar 2, and then minus the hypothesized value. The null hypothesis is always that the two means are equal, and so that means that there's a difference of 0. So it's always going to be 0 there. So if x bar 1 minus x bar 2 minus 0 over that standard error that we talked about before. The p-value happens the same way as it did before, and then the decision and conclusion also happen same way as before. All right, so there's a summary of the hypothesis testing situation for you. Okay, so now I'm going to stop this video and we'll come back and talk about pooled inference, whatever the heck that means.